Monoidal categories and their representations, Lecture 11, Module categories and functors. So from this lecture, we are starting our discussion of representations of monoidal categories. And to make a parallel first, let us recall what is a representation of an algebra. Let A be an algebra over some field K. Recall that a representation of A in a K-vector space V is an algebra homomorphism from our algebra A to the algebra of all linear endomorphisms of the vector space V. An alternative notion is a notion of an A module. Recall that a left A module structure on V is given by an action map from A times V to V, which has the following properties. First of all, this map is K bilinear. Then it is unital, which means that the element 1, the unit 1 of A, acts as the identity linear transformation of V. And then that this map is associative. It means that if we apply A to B times V, it should be equal to the application of AB to V. And it's a classical result in the usual representation theory that the notions of a module and of a representation are equivalent. So representations and modules are essentially the same things. The only difference is the accent how they are defined. A representation focuses on the homomorphism from A to the linear operators on V, while a module focuses more on the action. Recall also that a homomorphism between two modules is a linear map between the underlying vector spaces, which intertwines the corresponding actions of the algebra A. And using this, we can define the category of all A modules, where the objects are A modules and the morphisms are homomorphisms between A modules. So now let us try to define similar notions for monoidal categories. Let C be a monoidal category with a tensor product, identity object, associator, and two unitors. Let M be some category. Consider the monoidal category of all endomorphisms of M, that is the monoidal category of all endofunctors of the category M. So this is a strict monoidal category where the tensor product is given by the composition of functors and the identity object is the identity functor on M. Definition: a representation of C in the category M is a monoidal functor from our category C to the monoidal category of all endomorphisms of M. For example, for any C and any M, we have the trivial representation in which each object of C is represented by the identity endofunctor of M, and each morphism in C is represented by the identity natural transformation of the identity functor. So now we have defined the notion of a representation of monoidal category. Now let us define an analog of the notion of a module over a monoidal category. So we say that a category M is equipped with the structure of a left module category over C, provided that we are given the following data. First of all, we have the action bifunctor, which we denote by V times box, and this is a bifunctor from C times M to M. We have a natural isomorphism mu, which goes as follows. So if we have our action functor and on the left we have the tensor product in our category C, then there are two ways to bracket this expression. And mu should be a natural isomorphism from the bracketing where the bracket is on the left to the bracketing when the bracket is on the right. And finally, we also need a natural isomorphism L from I box times something, which is an endofunctor of M, to the identity endofunctor of M. So acting by the identity object should be isomorphic to the identity functor via a fixed isomorphism L. And these data are supposed to satisfy the following conditions. So there are two diagrams which will be given on the next slide, and these two diagrams are supposed to be commutative for all involved objects. So the first diagram, we take three objects x, y, and zeta in C, and we take an object m in M. So we can act on M by x tensor y and then tensor z. Now we can move the outer brackets using mu, and we end up in x tensor y acting on the outcome of z acting on M. And now we can again move the left bracket to the right using mu, and we get x acted on the outcome of y acting on the outcome of z acting on M. So this is one way on the diagram. The other way, so starting from x tensor y, tensor z acting on M, we can move the inner brackets to the right, and we get x tensor y tensor z acting on M. Now the outer brackets can be moved to the right using mu. We get x acting on the outcome of y tensor z acting on M. And then in the inner brackets, we use mu to move the inner bracket to the right to get x acted on the outcome of y acting on the outcome of z acting on M. So this diagram should commute. And for the second diagram, take any object x in C and any object m in M. So we have x times the identity acting on M. We can use mu to move the brackets to the right to get x acting on identity acting on M. So here we can use our L to go to x acted on M. Alternatively, starting from x tensor identity acted on M, we can use the right unitary row to go to x acted on M. And this diagram should commute. Just like in the case of associative algebras, it is very easy to see that the notions of a representation of C and a module category over C are equivalent. It's a very nice exercise to prove this equivalence. It is also a very interesting observation is that if you look at the axioms for monoidal functors, one of these axioms is a hexagon diagram, while the first diagram in the axioms of a module category is a pentagon diagram. So the connection here is due to the fact that the category of all endomorphisms of M is strict, and hence one side of the hexagon diagram collapses. So this defines the notion of a left module category. Similarly, one defines the notion of a right module category over C. And a right module category over C is exactly the same thing as a left module category over the category C reversed. So this is a category which was previously denoted by C op. This is the same category as C, but the order of the factors in the tensor product is swapped. Here is an example, and this is an example of a regular module. Let C be a monoidal category. Take as our module category M the original category C. Let box times be the tensor product in C, and let L be the left unitar lambda. Then all module axioms follow directly from the monoidal axioms, from the axioms of the monoidal category, and therefore this defines on C the structure of a C module. So this is called the left regular C module. And using tensor product on the right, we can define on C the structure of a right regular C module. The notion of an adjunction is very well adjusted to the notion of representation or a module category. So let C be a monoidal category and let M be a module category over C. Let x, y be a pair of adjoint objects in C. Then we can make the following observation. X box times with something, this is an endofunctor of M, and y box times with something, this is another endofunctor of M. So the observation is that this pair is a pair of adjoint endofunctors of M. Proof: the fact that x and y is a pair of adjoint objects in C means exactly that we have the corresponding unit and counit of the adjunction in C, which satisfy the adjunction axioms. And now these lift to a unit and co-unit of adjunctions for x box times something and y box times something, and these also satisfy the same adjunction axioms. And this implies that this pair is indeed a pair of adjoint endofunctors of M. This has the following interesting corollary. If C is a rigid monoidal category and M is an abelian module category over C, then every object X in C acts on M as an exact endofunctor. Indeed, if C is rigid, it means that each object X has both a left and a right adjoint in C, which means that the corresponding action endofunctor on M has both a left and the right adjoint as an endofunctor of M. But then it means that it must be exact. Next, let us discuss the notion of a submodule. So let C be a monoidal category, and let M be a module category over C. Definition: a module subcategory, or more informally a submodule, of M is a full subcategory N of M which is stable under the action of C. So this means that for any X in C and N in N, X box times N should be an object in N. So in other words, a module subcategory is a full subcategory stable under the action of C. For example, if C is a rigid monoidal category and M is an abelian module category over C, then the full subcategory P of projective objects in M is always stable under the action of C. Indeed, as we saw on the previous slide, if C is rigid, then any object in C acts as an exact endofunctor on M. And it has both left and right adjoint, which is again given by the action of some object in C. But this means that each X in C acts as a functor which is left adjoint to an exact functor. And any functor which is left adjoint to an exact functor sends projective objects to projective objects. So this completes the proof of this example. So we have now defined the notion of a left module and the notion of a right module. There is also a natural notion of a bimodule. Let C be a monoidal category and D be another monoidal category. Definition: we say that a category M is equipped with the structure of a CD bimodule category. This should be just CD bimodule category, over C is not necessary, provided that we are given a left C module category structure on M, a right D module category structure on M, and these two structures are connected by a natural isomorphism beta. So if we have an object in C, an object in M, and an object in D, so we can write the action with two different bracketings. And beta should be an isomorphism which moves brackets to the right. So if you take an object in M, first act by an element in C and then by an element in D, this should be isomorphic to the same object first acted upon by an element in D and then by an element in C via this fixed isomorphism beta. And this data should satisfy the following two conditions. So there are two diagrams which will be presented on the next slide, and they are supposed to be commutative for all involved objects. So here is the first diagram. So this is the tensor product for the left action. We start from an object in M, and then on the left we act by x tensor y, and then on the right by z. So we can move outer brackets to the right using beta to get x tensor y acted on M acted by that. And then we can use mu, the left mu, to move the left brackets to the right, and so we have x acted upon the outcome of y, acted upon the outcome of M, acted upon by z. Alternatively, we start from x tensor y acted on M, and then acted by that. And we use mu to move the inner brackets to the right. We have x acted upon, y acted upon m, and then on the whole thing we act by z. And here we use beta to move the outer brackets to the right. So we have x, and we act by it on the outcome of z acting upon the outcome of y acted on m. And here we use beta to move the inner brackets again to the right, and we end up in x acted on y acted on the outcome of z acting on m. So this diagram should commute. And we also have a similar diagram for the action on the right. So we have y tensor z on the right acting on the outcome of x acted on m on the left. So in our conventions for the right modules, so our isomorphisms, which are given by the structure, they always move brackets from the left to the right. So the correct rearrangement of this diagram is that we have the leftmost bracketing, so x acted on m, and then we act by y on the right and by z on the right. And from here, we can move the outer brackets to the right, and we end up x acted on m on the left, and then to this we apply y tensor z on the right. Now we move the left brackets to the right using beta, and we have x acted on the element obtained from m by acting with y tensor z on the right. And alternatively, we start from x acted on m, then we act by y and then by z. So we use beta to move the inner brackets to the right. So we start with m, act by y, then by x, then by z. Again, we use beta to move the outer brackets to the right. So we start with m, act by y, then by z, and then by x. And now we use the right mu to move the inner brackets here to the right, and we end up in m, acted on the right by y tensor z, and then we act by x. So these two diagrams should commute. And this is the definition of a notion of a bimodule over C. So we have now defined module categories. Let us define homomorphisms between module categories, and these are given by module functors. Let C be a monoidal category. Let M be a module category over C. Let M tilde be another module category over C. Definition: a module functor from M to M tilde is a tuple f, sigma, where f is a functor from M to M tilde, and sigma is a natural isomorphism from the bifunctor f applied to something box times with something, to the bifunctor something tilde box times with f applied to something. So this is the datum which defines a module functor, and this should satisfy again two axioms which are given by two diagrams on the next slide, which should commute. And also a small remark before we complete the definition: if we have a module functor which is an equivalence of underlying categories, this is usually called a C-module equivalence. So let's go back and complete the definition. We want now to present two diagrams, two axioms which should be satisfied by the datum which defines a module functor from M to M tilde. So the first diagram: for any x and y in C and any m in M, the following should commute. So we start with f applied to x tensor y acting on M. We use sigma to move the outer brackets to the right, so we end up in x tensor y, and then the tilde box times f of m. And now we can use mu to move the left brackets to the right, so we get x acted by tilde on y acted by tilde on f of m. This is one way in the diagram. And the other way, so we start with f applied to x tensor y acting on m. We use mu inside to go to f applied to x acting on y acting on m. Now we use sigma to go to x tilde acting on f of y acting on m. And now we use sigma here inside to go to x tilde acting on y tilde acting on f of m. So this diagram should commute. And the second diagram, for any m in M, we can start from f of the identity acting on M. We can use sigma to go to the identity acting by tilde on f of M. Now here we can use the L tilde, so this should be L tilde f of M to go to f of M. Alternatively, from f applied to identity acting on M, we can use f of L of M to go to f of M. And this diagram also should commute. Let us look at some easy examples. Example 1, let C be a monoidal category and M be a module category over C. Then the identity entofunctor of M has the obvious structure of a C module equivalence, where all sigmas are given by the identity morphisms. And in this case, both diagrams from the previous slides become trivial. And the second example, let C be a monoidal category, M a module category over C, and N a module subcategory of M. Then the inclusion functor from N to M has the obvious structure of a C module functor, where sigma is given by the identity morphisms, just like in the previous example. And again, in this case, both diagrams from the previous slide become trivial. So now we have defined morphisms between module categories. Next, we will define the notion of a morphism between morphisms. So these are called modifications. Let C be a monoidal category, and let M and M tilde be two module categories over C. Let F and F hat be two module functors from M to M tilde. Definition: a modification from F to F hat is a natural transformation zeta from F to F hat, such that the following diagram commutes. So we can start from f of x acting on M. Applying sigma, we go to x tilde acting on f of M. And now applying zeta m on the second factor, we go to x tilde acting on f hat of M. Alternatively, starting from f of x acting on M, we use zeta to go to f hat applied to x acting on M, and here we use sigma hat to go to x tilde acting on f hat of M. So this diagram should commute. Now we can define the bicategory of all C modules. Let C be a monoidal category. We can now define the bicategory. A bicategory is a monoidal category with several objects, which is usually denoted by C mod with capital M, and this is a bicategory of all module categories over C. The objects in this bicategory are all module categories over C. One morphisms are module functors between these module categories, and two morphisms are modifications. The identities are the identity functors and the identity natural transformations, and the composition is given by the composition of functors and the composition of natural transformations. In particular, for any two module categories M and N over C, we have the category Hom CMN of all module functors from M to N, where the morphisms are modifications between module functors. Let us discuss some further examples. Example, let K be a field, let A be a finite dimensional associative K algebra. Then we can consider the corresponding monoidal category of all finite dimensional AA bimodules. Then the claim is that the category of all finite dimensional A modules is a module category over the category of all finite dimensional AA bimodules. So here, the action is given by the tensor product over A, and the isomorphism mu is given by moving the brackets in the tensor product from left to right. So x tensor y tensor z is sent by mu to x tensor y tensor z. And the map L is given by the multiplication map. Here's another example about module functors and modifications. Let C be a monoidal category. Fix an object Q in C and consider the left regular C module C. Then we have the endofunctor of C, which is given by tensoring with Q on the right. And the claim is that this endofunctor has a natural structure of a C module endomorphism of our left regular C module. So here, the map sigma, which starts with X tensor M and then tensors with Q, and ends in X tensor M tensor Q, is simply given by our associator alpha. One can say even more. If we fix another object Q tilde, then we have the corresponding endofunctor tensoring with Q tilde on the right. So this is another C module endomorphism of C. Then for any morphism F from Q to Q tilde, tensoring on the right with F is a modification from tensoring on the right with Q to tensoring on the right with Q tilde. So here is an example how we can construct C module functors and modifications between them. Now let us briefly discuss the notion of a quotient for representations. Let's see be a monoidal category and M a module category over C. Recall that a congruence on M is a collection of equivalence relations on each home space from an object M to an object N in M. So we take this collection of equivalence relations, which we denote by sim. So for each object M and N, we have an equivalence relation sim M, N on the corresponding home set. And this collection of equivalence relations should be stable under both left and right composition. In other words, if F is equivalent to G, then HF should be equivalent to HG for any H for which the expression makes sense, and FU should be equivalent to GU for any U for which the expression makes sense. Given a congruence on M, we have the quotient of M modulo this congruence, which is the category which has the same objects as M, but where the morphisms are exactly the equivalence classes of morphisms in M with respect to our equivalence relation, with respect to our congruence. A congruence on M is called C-stable, provided that for any F in G, so if F is equivalent to G, then acting on F by some morphism nu in C gives a morphism which is equivalent to the morphism obtained from G by acting on G via nu. And this should be true for any morphism nu in C. In particular, this means that if F is equivalent to G, then X of F is equivalent to X of G for any morphism X in C. So we can take nu to be the identity endomorphism of X and plug it here to get this equality. So if a congruence sim on M is C-stable, then the corresponding quotient naturally inherits from M the structure of a C module category. So this is how you form quotients of module categories. So here's an example. Let C be a rigid monoidal category and M be a module category over C. Let us assume that M is equivalent to the category of finite dimensional modules for some finite dimensional associative K algebra A. Then we have already seen that the category of projective objects in M is a C module subcategory. Let us now define the equivalence relation on M as follows. We call two morphisms equivalent if they are different factors through some object in proj of M. This is obviously a C-stable congruence because proj of M is C-stable. So we can consider the quotient of M by proj of M. This is usually called the stable category of A. And we have on this quotient the induced structure of a C module category. So here is another example related now to bimodules. Let C and C tilde be two monoidal categories, and let F be a monoidal functor from C to C tilde. Then C tilde has a natural structure of a CC bimodule category, where the left action by X is defined as f of X and then tilde tensor with M. The right action of C is defined as follows. An object y in C acts on the right of M via M tilde tensor with f of y. And the rest of the structure is defined using the associators and the unitors in C tilde. And all axioms follow directly from the axioms of monoidal categories and monoidal functors. So let us finish with some problems and questions. Question 1. Check with all details that the notions of a representation of and a module category over a monoidal category are equivalent. Question 2. Define with all details the notion of a right module category over C. Question 3. Prove that if C is rigid and M is abelian, then the full subcategory I of injective objects in M is stable under the action of C. Question 4. Spell out all details in the definition of C mod. And question 5. Check all details in the example of module endofunctors and modifications for the left regular C module. Thank you very much and see you next time.